our today's lecture on the design of reinforced concrete retaining walls. If you have any questions, please ask your questions in the previous lectures. Any question? Okay, if there are no questions, then we will go ahead. The topics which will be addressed in today's lecture are introduction to retaining walls, some terms related to retaining walls, types of retaining walls, soil parameters, earth pressure for normal conditions of loading, retaining wall failure, drainage, and other details, and design of one cantilever reinforced concrete retaining wall. There are many terms that you would have already studied, and you will be familiar with those terms because you, I suppose, have already studied these things in some of your geotechnical courses. This lecture is not meant for introducing all those terms to you. This lecture is only, has been devised in such a manner that you will be able to design one reinforced concrete retaining walls, but along with that, you will also be able to classify some types of retaining walls, and the failure mechanism of retaining wall will also be discussed. Okay. You know that retaining walls are used to hold back masses of earth or other loose material. And they are used in the construction of railways, highways, bridges, canals, basement walls, in buildings, walls of underground reservoirs and swimming pools. So they are one of the important components in structural engineering. These are a few retaining walls shown in pictures. On the top left, you can see retaining walls, which is a retaining wall, basically a kind of composite retaining wall made with stones and vertical concrete elements. You can also see some holes. These holes are called as weep holes in order to release pore water pressure from the backfill, if there is any, because the rainwater will percolate on the backfill side, and they may create pore water pressure. In order to release that pore water pressure, weep holes are provided in almost all retaining walls. This is another guide of retaining wall. You can see this is a reinforced concrete retaining wall. In the top middle picture, you can see retaining wall, stone masonry retaining wall with some damage to the retaining wall also can be noticed. Then in the top right, you can see a reinforcement for a retaining wall, reinforced concrete retaining wall. The bottom right picture is a retaining wall, reinforced concrete retaining wall with counterfort retaining wall. And this is basically an abutment of a bridge, because abutment of a bridge is also more or less like retaining wall. Counterforts are provided. Counterforts are these elements which are provided in order to increase the load carrying capacity of the retaining wall, lateral load carrying capacity of the retaining wall, and also to prevent sliding and overturning of the retaining wall. Some terms related to the retaining wall are explained in this slide. You will be able to see backfill. Backfill is the material which is to be retained or held back, and surcharge is any load on top of the backfill in terms of vehicular live load or some other load stored over and above the backfill. Like, for example, a truck of sand unloaded on the backfill. Backfill will give us a surcharge load in a triangular pattern. The surcharge, it is very obvious that any load over and above the backfill, which is called a surcharge, will also increase the pressure on the retaining wall. Okay, the typical reinforced concrete retaining wall has these components. The vertical components, which is used to hold back mass of the earth or other loose material, is called as arm or stem. This can have a non-prismatic shape as shown in this figure, with the smaller dimension, small thickness at the top, and wide section at the bottom. But this can be uniform section as well, depending on the situation. Because in most of the cases, In almost all the cases, there will be maximum bending moment at the base of the arm or stem. So in order to increase the flexure stiffness of the arm or stem, the width at the base of the arm is kept the highest, and with the and then it is gradually decreased as we move up to the top part of the arm or stem. The back, this heel and toe collectively is called is base of the retaining wall. The back portion of the retaining wall base is called as heel part, and this is the front wall is called as toe part. Sometimes the key is also provided, which is inserted inside the ground in order to increase the sliding capacity, in order to increase the capacity of the retaining wall against sliding. Okay. You know that soil will exert pressure in triangular pattern as shown in this figure. You know these things from your technical understanding. And the backfill will also exert a vertical load due to gravity on the heel, and the heel will be pushed down. And in return, the heel will be this load of the backfill acting downward will be resisted by the soil beneath the heel, and this will be pushed up. This will be the backfill will push the heel down. Similarly, the toe will also be pushed up. The toe will be pushed up because when you can imagine that when the retaining wall moves forward, the heel will be pushed down and the toe will be pushed up. Okay, and the key will be pushed back. So if you want to draw a deformed shape of this, the deformed shape will be like this. The heel will be pushed down because of the backfill weight. The toe will be pushed up due to the pressure of the soil. The key will be pushed back because the whole retaining wall, if it tends to move forward, the key will be pushed back. And the retaining wall itself will bend forward with tensile stresses at the back side of the retaining wall on the backfill side. In the heel, the tensile stress will be produced in the upper side of the heel. In the toe, the retaining in the toe, the tensile stress will be produced on the lower part of the toe. In the key, the tensile stress will be provided on the front side of the key, not on the back side, the front side of the key. So if you want to place reinforcing bars in the different components of the retaining wall, they must be placed in this in these locations. In the arm part, this will be placed on the backfill part of backfill side, which is called the back side of the retaining wall, the heel, top side of the heel, the bottom side of the toe, and the front side of the key. So this will be the main reinforcement required in a reinforced concrete retaining wall. Okay. In all other parts of the retaining wall, the reinforcement will be placed according to the ACI code criteria, which will be discussed in the next slides. Some types of retaining walls. These are typical types of retaining wall. A typical type of retaining wall is a gravity wall, which is used for small heights up to 10 feet or so. And these retaining walls are called as gravity wall because they resist all the actions coming from the retained soil due to the weight of the retaining wall. And these retaining walls are mostly constructed constructed in stone masonry. So the stone masonry retaining walls are gravity retaining walls, and these retaining walls resist all the actions produced by the soil due to the lateral movement of the soil. These retaining walls resist all these actions by the weight of the retaining wall, only the weight of the retaining wall. So they don't have any bending stresses, bending resistance. They resist all the actions merely by the weight of the retaining wall. Okay. They are used in small heights because for very tall retaining walls, they are not recommendable for the reason that the size of the retaining wall will become too big, and in order to accommodate big retaining walls in a limited space will become a challenge. Therefore, reinforced concrete retaining walls are then used for for tall retaining walls. In the case of a very tall retaining wall, reinforced concrete retaining wall with thin sizes as compared to gravity wall can be used as shown in this figure, with the arm with much less dimension as compared to the gravity wall and heel and toe. However, the cost of reinforced concrete retaining wall may be much higher than the gravity retaining wall. We recently concluded a project for the CNW department where we have proposed several types of retaining walls for different conditions, and they are called as modular designs for different heights, up to 10 feet or up to 15 feet. We have proposed stone masonry retaining walls, then plumb concrete retaining. Plumb concrete is a type of concrete where big boulders are placed inside a grout type of cement slurry and grout in the stone masonry. The stone masonry with the grout and slurry is called as plumb concrete. So the plumb concrete retaining wall we have designed for them, and the stone masonry retaining walls and the reinforced concrete retaining walls for different conditions. Okay, with the slope side towards the backfill or away from the backfill, there are different conditions and different advantages, disadvantages of all these walls. So in order while taking into consideration all these advantages and disadvantages of different types of retaining walls, we have proposed several retaining walls to the CNW department so that they can use it wherever these retaining walls are required. And the economy is being also taken into consideration so that the retaining wall is not too expensive where it is provided. Okay, then there's a third type of retaining wall, which is called as counterfort retaining walls. This is a counterfort retaining wall shown in the figure. You will also see details of this. This is a counterfort retaining walls. Okay, drainage is also a very important thing to be considered in the design of retaining walls, because most of the retaining walls fail due to the improper drainage on the backside of the retaining wall or at the bottom of the backfill. You can see a tile drain has been provided in this gravity retaining wall along the length of the retaining wall in order to release the pore water pressure, in order to prevent the seepage of water beneath the base of the retaining wall. Similarly, in this retaining wall also, a tile drain has been provided on the back side of the arm in order to prevent the seepage of water to the base of the foundation and also to release the pore water pressure. Weep holes are also provided in almost all retaining walls. As you can see, some weep holes here in this figure, and you've also seen the weep holes in one of the figures in the previous slides. Okay, some of the soil parameters, these are approximate soil parameters which when required can be used, but it is advised to use the lab test data for these soil parameters. These soil parameters have been taken from geotechnical books, and it's the different types of soil have been classified according to the classification of typical geotechnical classification. There are 5 types of soil discussed in this table, and corresponding to every soil type, the unit weight of the soil, the angle of internal friction, and F is the coefficient of friction between the base of the retaining wall, which is mostly concrete, and the soil. And this factor is important for the sliding resistance to calculate for the calculation of sliding resistance of the retaining wall. Okay, if soil is sand or gravel without fine particle, highly permeable soil, then the unit weight of the soil can be taken from 110 to 120 pound per cubic foot. The angle of internal friction or phi can be taken from 33 to 40 degree, and the coefficient of friction between the base of the retaining wall and the soil may be taken from 0.5 to 0.6. And similarly, for all other different types of soil, these parameters have been taken. You can study these parameters yourself in detail later. Okay. Okay, these top three types of soil, they are very good for as a backfill because they include sand, and sand will allow water to sands are permeable. They will allow soil to percolate inside the soil, and they will be the water will be then collected by the tire head on the backside of the backfill, and it can be disposed where required. Unlike the clay type of soil, which will retain soil in the pores of the clay, and it will create a pore water pressure on the retaining wall, and this pore water pressure can sometimes may be very dangerous for the retaining wall. Okay, different types of loading condition of the soil. In the figure A, the soil is acting. The backfill is acting on the retaining wall, and you know that the pressure diagram will be triangular in pattern. Okay, this triangular distribution of the lateral pressure is shown in the figure. The resultant of this can be very easily calculated from this triangular distribution of the pressure diagram, and P will be equal to half of KH, where K is the active earth pressure, and gamma is the density of soil, and H is the height of the backfill, and P will act at a distance of H by 3 from the base of the retaining wall. Similarly, if we have a backfill, and on top of the backfill there is a surcharge which makes an angle of lambda with the top of the retaining wall, then P can be calculated from this equation, Y can be calculated from this equation, and for lambda is equal to phi, K active pressure can be taken as cos of phi. You know these things, you would have studied these things in your technical book. If you don't remember these derivation and these equations, you better get hold of any good book on geotechnical engineering, soil mechanics book, and you will be able to see not only these equations but also the derivation of these equations. Okay, then there is a third condition where there is a backfill. The backfill variation is triangular, but on top of the backfill there is uniformly distributed surcharge with surcharge S in pound per square foot. Then this surcharge can be converted into equivalent height H prime, and this can be calculated by this equation. S is equal to gamma S. S is the surcharge pressure in pound per square foot, and gamma is the density of the soil. So this will give us H prime in feet or in inches, whatever the units are, and then the triangular distribution can be transferred. The trapezoidal distribution of the backfill can be transformed into a triangular distribution like this. Okay, then P can be calculated from this equation, Y can be calculated, and so on. Because these things will be needed in the next slide, so it is better to revise these things, although you have studied these things in your technical course. Next, I will share with you a video which is a very useful video, and you can also find other videos from this source which are very, very useful for students, and I hope many of your concepts will be clarified with this video. You can further watch other videos from this source.
Retaining walls serve the important role of holding back soil and rock, just as dams hold back water. The first video in this series showed that granular materials such as soil and rock generate horizontal pressures that increase linearly with depth. Retaining walls must resist these pressures, and many strategies exist for doing so. In this video, we focus on the popular L-shaped cantilever design. If you were going to use an L-shaped wall to hold back soil and rock, as represented by these marbles, would you point the bottom leg towards the marbles or away from them? Many people would say that the base of the L should face away from the marbles. They probably realize that it is hard to tip the wall over towards the left if the bottom leg points in that direction. In engineering, we call tipping like this overturning. If the bottom leg points the other way around, it is easy to make the wall overturn. So easy, in fact, that I can do it with just a puff of air. It looks like the case is closed. Or is it? Before we declare a final verdict, let's use the model to find out what happens when the bottom leg points to the left, away from the marbles. As we add marbles, we discovered that the horizontal forces they produce create yet another mode of failure, namely sliding of the wall. And this occurs when the marbles reach a depth of 3 centimeters. In the model, we can increase the friction between the retaining wall and the base by placing a rubber mat between them. You will have to do some extra reading if you want to find out how they achieve this end in the real world. As you can see, increasing the friction allows our model wall to support a noticeably greater depth of marbles, but it still eventually fails by overturning, in this case, when the depth reaches 8 centimeters. Now let's turn the wall around, so its bottom leg points towards the right, the side where the marbles will be placed. We again use a rubber sheet to prevent sliding, and we add some marbles. As before, the marbles generate a horizontal force that depends on the marble depth. You might be surprised that this wall can hold back 11 centimeters of marbles before it overturns. Can you explain why the wall can resist a greater height of marbles when the bottom leg points towards them? Is there an additional force that comes into play? Recall that granular materials generate both horizontal and vertical pressures. When the bottom leg is oriented away from the marbles, overturning is resisted only by the weight of the wall itself, and so it overturns easily. When the bottom leg points towards the marbles, the vertical pressure from the marbles helps to keep the wall upright. The downward pressure also increases the friction between the bottom of the wall and the ground, thereby reducing the likelihood of sliding. When engineers design L-shaped retaining walls, they imagine them overturning about the point labeled Q. They first calculate how strongly the soil pressure will tend to make the wall rotate about Q. We call this tendency to tip an overturning moment, and we label it MO. Next, they figure out the stabilizing moment, MS, produced by the soil pushing downwards on the horizontal leg of the wall. Lastly, they make sure that the horizontal leg is long enough that the stabilizing moment is at least as large as the overturning moment. Then the retaining wall will be stable. You might be surprised to learn that L-shaped walls are seldom used as dams. The reason is that pressurized water at the bottom of the dam can seep under the base of the dam. And if it does, the resulting upward water pressure on the bottom of the dam can generate an additional moment and make the dam overturn. Lots of other clever approaches can be used to design retaining walls, but we do not have time to discuss them here. To learn more about how soil, water, and other materials interact with structures, we hope you will view our videos on dams, silos and tanks, and tunnels and culverts.
Okay, so next we will discuss the retaining wall failure. A typical reinforced concrete retaining wall may fail in 3 different ways. And this needs your attention now to understand the failure modes. In a reinforced concrete retaining wall, the first failure mode is the individual structural parts of the wall may fail, and they may not be strong enough to resist acting forces. This is called a structural failure. Because structural parts will fail due to insufficient reinforcement or insufficient size of the retaining wall. Any part of the retaining wall or all parts of the retaining wall, for example, arm, heel and toe or key, any one of these are more than one of these parts or all of these parts may fail due to insufficient reinforcement or insufficient size. If this happens, this will be called a structural failure. The second kind of failure is called a stability failure. The stability failure can be of 2 types: overturning, as we have seen in the previous slides, and sliding. The third kind of failure, which was not discussed in the previous video, may be due to the soil settlement. If the soil underneath the retaining wall is not strong enough to take the load of the retaining wall, in the case of horizontal pressure. When horizontal pressure increases and the retaining wall, the retaining wall will tend to uh, apply pressure on the soil beneath the retaining wall on the toe side, and there can be settlement of the soil due to the increased pressure from the toe. This will be called as failure of the soil or soil settlement. So these three kind of failure will happen in the case of retaining wall. In all these three types of failure shall be avoided in the design of retaining wall. The failure of individual parts of the retaining wall can be avoided if stem, heel, and toe are designed according to the ACI code. As you can see on this slide, that stem, heel, or toe of the retaining wall may fail in bending and shear, such as when a vertical cantilever wall is cracked by the earth pressure acting on it. The design of these components require the determination of the necessary dimensions and sizes, thicknesses, and reinforcement to resist the moments and shear. The usual load factor and strength reduction factor of the ACI code may be applied. The ACI load factors relating to the structural design of retaining walls are summarized below. This is from the ACI 5.3.1. A factor of 1.6 is used for horizontal pressure, 1.6. So as you can see from the table below, that the pressure of the soil, the load factor is 1.6, and it is denoted by H. So there is an additional term. Previously, you know 1.2D plus 1.6L, so additional terms of 1.6 times H will be used wherever there is a soil pressure on the retaining wall, uh, any part of the retaining wall. Okay, the weight of all the retaining wall components will be multiplied by 1.2, because, as you know, that it is dead load of the dead load is always multiplied by 1.2, and the horizontal pressure from the backfill is treated like a live load. Therefore, it is multiplied by 1.6. Only one thing shall be noted in this slide, that is the weight of the toe slab. As you have seen in the one of the previous slides, the toe slab will be pushed upward by the soil pressure, and any weight of the toe slab itself or of any material on top of the toe slab will reduce this pressure. And we would like to design toe slab on the conservative side, so that it does not fail due to the pressure from the soil. Therefore, in most of our calculations, we ignore weight of the toe slab and weight of the soil. However, if weight of the toe slab is to be considered in the design, it is multiplied by 0.9 instead of 1.2, because in this case, weight of the toe slab will reduce the pressure of the soil and also the bending moment, the ultimate bending moment on the toe. For this reason, it will not be amplified, whether it will be de-amplified. Okay, these are different recommendations on the reinforcement by the ACI code. The longitudinal, the vertical reinforcement on the back side of the retaining wall is the main reinforcement in the arm or stem. This reinforcement shall not be less than AS minimum, which we have used for beams. And similarly, the top side of the heel will also have main reinforcement. The bottom side of the toe will have main reinforcement, and all these reinforcement in the arm, main reinforcement in the arm on the back side, heel on the top, toe on the bottom shall not be less than this minimum reinforcement. And this minimum reinforcement equation is the same as the one we have used in the case of beams. Okay, and maximum spacing for both horizontal and vertical reinforcement shall not be more than 3H or 18H. Okay, on the other parts of the retaining wall, in the arm, the front side of the retaining wall, the vertical reinforcement on the front side shall be 0.0015 of gross area, and the horizontal reinforcement along the length of the retaining wall on the back side of the retaining wall shall be equal to 0.0025 Ag according to the ACI code. Okay, and in all other places, the reinforcement will be used as supporting bars at the rate of number 4, at the rate of 18 centimeters will be more than enough in order to hold this reinforcement. Okay, to safeguard the wall against bodily displacement, that is to ensure its external stability, The overall factors of safety is evaluated by comparing resisting forces to maximum load acting under service conditions. Okay, as you have seen in the video, the lateral pressure will push the retaining wall forward, will cause sliding of the retaining wall, as well as overturning of the retaining wall. You can see from this figure that the overturning moment is P times this distance, which is Y. So Py is the overturning moment, and summation of W, which is the weight of the components of the retaining wall, as well as the weight of the backfill, times this distance A. This will be the stabilizing moment. This will cause the stabilizing moment. The stabilizing moment given by summation of W into A shall be 1.5 times more than the overturning moment. So the factor of safety 1.5 shall be maintained in the overturning of the retaining wall. So in the form of equation, this can be written like this: summation of W, which is the summation of all the weights, times the A, which is the distance of this resultant, RV. RV is the summation of W. So the resultant of all the weights is being denoted by RV, which is RV means vertical resistance, I mean, due to all weights. So this this multiplied by A, because the overturning, as we have seen in the video, will occur at this point, at the tip of the heel, at the tip of the tip of toe here at this location, divided by Py, which is the overturning moment, must be greater than 1.5, whereas the distance of the resultant summation of W are equal to RV from the toe. Similarly, you can also see that this P will cause sliding. And the sliding will be resisted by the resistance force, which will be produced by the summation of W equal to RV multiplied by the coefficient of friction between the soil and the base of the footing. So summation of W or RV multiplied by mu or F, which is the coefficient of friction between the soil and the base, divided by P, which is the sliding force, must be greater than 1.5, so that 1.5 factor of safety is also maintained against sliding. This will ensure that the retaining wall is stable and will not overturn or slide. Okay, the determination of small a, which is the distance of RV or summation of W from the tip of the toe, is demonstrated in this slide. You know that RV, if RV is, let's say, acting, which is the resultant of all these weights acting downward, let's say this RV is acting at a distance of A from the point O, then RV times A, it is a stabilizing moment, plus P times Y, which is the overturning moment, must be equal to W1x1 plus W2x2 plus W this in all this, where RV is summation of all these weights. Therefore, small a can be very easily calculated from this equation, which is Wx1 all this minus Py divided by RV summation of W. So small a can be calculated from this equation. Once small a is calculated, we exactly know the location of the resultant RV from the point O. And this is important to be calculated in order to calculate the stabilizing moment, which is summation of W times A. If the third kind of failure of the retaining wall, as we have discussed in the previous slide, is the failure of soil beneath the wall. If the pressure of the wall on the soil beneath exceeds the maximum allowable limit, the soil beneath the wall may fail. Computed soil bearing pressures for service load conditions are compared with allowable values set suitably lower than ultimate bearing values. Okay. These bearing pressure at the beneath the toe will be maximum. This is a condition where there is no backfill, so this is not a condition of basically of the retaining wall, but just for the purpose of discussion, this has been included. If there is no backfill, the total weight RV will act at such a location that the pressure distribution will be rectangular. And if there is a backfill pressure in the form of P, then this backfill pressure will change the upward pressure of the soil in this manner, so that at the front side of the retaining wall, there will be more pressure, and on the back side of the retaining wall and the hillside, there will be less pressure, giving rise to a trapezoidal distribution of the pressure from the soil. So, and there can be another condition, and in every condition, the resultant R has been shown. The resultant R in the second case falls within the middle third. If the base of the retaining wall is divided into three equal parts, the middle part, the middle third part is called middle third. So if resultant falls within the middle third, then the distribution will be like this. And whether the resultant falls within the middle third or outside of the middle third has a lot of implication on the stability of the retaining wall. And this will happen, the resultant, whether the resultant falls within the middle third or outside middle third, this will depend on the relative values of the horizontal pressure and the weight of the retaining wall and the backfill. If the weight of the backfill and the horizontal pressure is such that the resultant falls at the edge of the middle third, then this will be the condition. A triangular kind of distribution of the soil pressure will occur with zero pressure below the heel and maximum pressure below the toe. In this condition, R falls outside the middle third, and in this condition, part of the retaining wall is being lifted up because P pressure is much higher than the vertical stabilizing force. Therefore, some part of the retaining wall is not in contact. This part of the retaining wall is in fact not in contact with the soil. Therefore, the distribution of the soil will be like this. In every case, the pressure beneath the toe, this ordinate shall be calculated, and this will be compared with the allowable bearing capacity of the soil in order to see whether the soil will settle or not. Okay, if the condition is such that R falls within the middle third, which is case number 2, Q1 and Q2 can be calculated from these equations, and these equations are available in almost every geotechnical book. Okay, Q1 is the maximum pressure beneath the toe, and Q2 is the minimum pressure beneath the heel. Q1, Q2 can be calculated from this equation. Okay, if resultant R falls at the edge of the middle third, then the Q1 and Q2 can be calculated. Q2 is 0 and Q1 can be calculated by this equation. If R falls outside the middle third, then Q2 is already 0 and Q1 is 2RV divided by 3A. So for all these conditions, Q1 can be calculated, which is the maximum bearing pressure beneath the toe, and this maximum bearing pressure shall be compared with the allowable bearing capacity. If maximum bearing pressure below the toe is less than the allowable bearing capacity, then there will be retaining wall will be safe. There will be no problem of the settlement of retaining wall. It is generally good practice to have the resultant located within the middle third. If as is mostly the case, the resultant strikes within the middle third, adequate safety against overturning exists and no special check will be made. So this point shall be noted. If resultant is within the middle third, then the overturning will not occur. Sliding may occur, but the overturning will not occur. This is for sure. If the resultant is located outside the middle third, a factor of safety of at least 1.5 should be maintained against overturning. So this point shall be noted. The most common failure reasons of the retaining wall have been discussed on this slide. The failures or damage to retaining walls in most cases occur due to one of the two following reasons. Number one is overloading of the soil under the wall with consequent forward tipping, which is the soil failure. So the soil bearing capacity failure or the soil settlement is one of the most common reasons, and that is what we have also observed in the project of modular design of retaining wall for CNW. That in most of the cases, the settlement of the soil was the major problem, especially in the case of gravity retaining wall, where the wall weight is much higher as compared to a cantilever reinforced concrete retaining wall. And the other reason is insufficient drainage of the backfill. So in order to take care of these two problems, allowable bearing pressure should be selected with great care. and soil immediately underlying the footing and the deeper layer should necessarily be investigated in order to prevent the failure of retaining wall due to these reasons. The drainage is discussed in the previous slides, can be provided in several ways in the form of weep holes, in the form of a tile drain at the back side of the retaining wall in this form. Okay. Next is an example of a reinforced concrete retaining wall. The total height of the retaining wall is 15 feet, but the soil to be retained is 11 feet and 6 inch. And the other parameters are also given in this slide. The unit weight of the soil 120 pound per cubic foot, angle of internal friction 30 degree, and base friction coefficient F is equal to 0.6, active pressure is 0.33, and base pressure is 3. There is a surcharge of 400 pound per square foot, and the density of concrete which is to be used in the design of retaining wall is 150 pound per cubic foot with compressive strength of 4500 psi and yield strength of 60,000 psi. The allowable bearing pressure is 8,000 psf or 8 ksf. This is the data given. We are required to design this retaining wall. We will be designing this retaining wall against all the failure modes. Okay, first of all, to fix the size of the retaining wall, we will use thumb rule. This thumb rule is, in most of the cases, this works very well. The top of the retaining wall can be taken from 8 to 12 inch. The bottom of the arm or stem, the width at the bottom of the arm can be taken is h by 15 to h by 10. For example, if the 10 feet is the height of the retaining wall, so and if you want to take h by 15, this will be 1.5 feet. If you want to use h by 10, this will be 1 feet. Any value from h by 15 to h by 10 can be used for the sizes at the base of the stem. Okay, the total length of the base of the retaining wall can be taken, can be assumed from 0.4 h to 0.65. For example, if h is 10 feet, this can be 0.4. This can be 4 feet and r 6.5 feet. So any value between 4 to 6.5 feet can be assumed for the length of the base of the retaining wall. Sorry. The thickness of the base can be taken from this equation, h by 15 to h by 10. Okay, and the size of the toe can be fixed from b by 3, the 1/3 of the length of the base, which is 1/3 of the length of the base, the size of the toe. So this will give us a good head start, and then we can check the retaining wall, and if there is any problem, we can change the size of the retaining wall. Okay, so let's assume that we take the length of the base of the retaining wall equal to 0.65 h, which is 0.65 into 15, 9.75 feet. So base of the retaining wall is 9.75 feet. And the thickness of the retaining wall, the thickness of the base of the retaining wall is taken as h by 10. H by 10 is 1.5 feet. Top width of the arm is taken as 8 inch. And the width of the arm at the bottom here at this location is taken as h by 12. Any value between those recommended can be taken, or any other value can also be assumed depending on the situation. But finally, we will have to check whether the size of the retaining wall is sufficient or not. If it is insufficient, we will change the size according to the requirement. The length of toe of retaining wall is b by 3, and 9.75 divided by 3 is 3.25 feet. The equivalent depth of surcharge is 400 pound per square foot or 0.4 kip per square foot. It will be divided by the density of the soil of the surcharge, which is 0.12, and equivalent height h prime 3.33 feet can be used in order to simulate the surcharge by the triangular distribution of the backfill. Like this. The triangular distribution, the surcharge has been transformed into this triangular distribution, and this triangular distribution, from this triangular distribution, P can be calculated from this equation, Y can be calculated from this equation. The P value when calculated from this equation, because everything is known to us in this equation, active pressure, gamma, H, H prime, P comes out to be 6.49 kip, which is the resultant of this triangular distribution of the soil, both by the backfill and surcharge. Y is the point of application of this force P from the bottom of the retaining wall. This is calculated from this equation, and it comes out to be 5.77 feet. And the overturning moment can then be calculated. Overturning moment is PA times Y, so this is 37.45 foot kip. Now, when overturning moment has been calculated, we can then determine the stabilizing moment, provided we calculate the point of application of the resultant RV, which is the summation of all the weights acting downward. So from all the weights which are acting downward, W1, which is the weight of the arm, is being divided into two parts, one rectangular and the other triangular part. W1 is rectangle, W2 is triangular part, W6 is the weight of the backfill rectangular form, and W5 is a triangular form, W3 is the weight of the base. And all these weights multiply by the weights have been calculated from the area and the relevant density of the material. The weights have been calculated and the weights are acting downward, and all the weights, the point of application of the weight is known to us. The distance from the point O, which is the tip of the toe, can also be calculated with a little effort. So when these weights multiply by the distances are calculated, summation of Wx, then summation of Wx comes out to be 96.84 kip. Just for the sake of demonstration, I will discuss the weight W1, which is the weight of the rectangular part of the arm. W1, you know that it is 8" at the top. Okay, so when we draw a line in this form, this triangle will have this side 8", and the height of this rectangle, the height of this rectangle will be equal to 13.5 feet. 13.5 feet from the top of the base of the retaining wall, from this location. And the width of this rectangle is 8". So 8" divided by 12, this will convert into feet. Multiply by 13.5, this will come out to be the area of this rectangle. And W is equal to gamma A. Gamma is 0.15. 0.15 multiplied by 9 will give us 1.35 weight of this rectangular part of the arm. And the distance of this can be calculated because W1 will act at the center of this rectangle, and the distance from the toe to this center can be very easily calculated, which is 3.5 feet. So 1.35 into 3.5 feet, this will give us Wx. For all other weights, this can be done very easily. And the summation of all weights will give us RV, and summation of all weights is equal to RV is equal to 16 kip. The stabilizing moment is 96.84 kip. Okay, so first of all, we will determine factor of safety against overturning, which is summation of Wx divided by the overturning moment, which is 96.84 divided by 37.45. This is 2.58 greater than 1.5. Factor of safety against sliding is F multiplied by RV divided by PA. Total horizontal sliding force is 6.49 kip, which we have calculated in the previous slide. And distance of sliding is 0.6 into 16, 9.6 kips. Factor of safety against sliding is calculated from this ratio of sliding force to the horizontal force, which is coming from the backfill. So this comes out to be 1.47. This is slightly less than 1.5. So this will work. However, if you want to increase this ratio, we can provide sliding, or we can also increase the size of the heel, which will increase the weight of the soil. And by increasing the weight of the soil, the RV will increase. And when RV increases, then this ratio will also increase. Or we can also provide a key. Okay. Next, we will calculate small a, which is the location of the resultant R, from point B, which is the tip of the toe, And we have demonstrated this in the previous slide. This can be done by this equation: A is equal to summation of Wx minus overturning moment divided by R. This comes out to be 3.71 feet. So from this, when small a is 3.71 feet, and this 1/3 of the base of the retaining wall, 1/3 of the base of the retaining wall is 3.25 feet. It means that R falls within the middle third, because 3.71 is small a, and if small a is more than this distance L by 3, it means that R falls within the middle third. And we have discussed in the previous slide that it is a favorable condition when R falls within the middle third, because then you don't have to check the overturning, you don't have to check the retaining wall against overturning, because when R falls within the middle third, it is for sure that a retaining wall will be safe against overturning. Although we have done this in the previous slide just for the purpose of demonstration. Now we can also determine Q1 and Q2 in order to check the retaining wall against any soil settlement. Q1 is the bearing pressure below the toe, and Q2 is the bearing pressure below the heel. Q1 can be calculated from this equation. Everything in this equation is known to us. When Q1 is calculated from this equation, Q1 comes out to be 2.8 kip per square. So this ordinate comes out to be 2.8 kip per square foot, in the ordinate below the heel comes out compared with the bearing pressure, allowable bearing capacity of the soil. If allowable bearing capacity is more than Q1, then the soil will not settle, and the retaining wall is safe against the soil settlement. So, and if it does not happen, then we will increase the base of the retaining wall in order to decrease Q1. Okay, in our case, this is safe. So finally, we have selected these dimensions. With these dimensions and the checks against the stability, all the checks against stability have been made, and we have found that the retaining wall is safe against overturning, against sliding, and also against soil settlement. So the final part of this design of the retaining wall will be checking the arm, heel, and toe separately against the structural failure. So now we will design the arm, heel, and toe for structural adequacy. For structural adequacy, it is important to calculate loads on different parts of the retaining wall. First of all, we will calculate load on the heel and the toe of the retaining wall. We will ignore the weight of the toe, because the toe will, any weight of the toe or weight of the soil on the toe will act downward. And when this act downward and the soil pressure act upwards, and the soil pressure upward will give us the bending moment at the toe and the junction of the arm. If the weight of toe and weight of the soil above the toe is ignored, so this will be conservative. It will give more reinforcement, which is good for the purpose of design of toe. Okay, so this weight of the toe and weight of the soil on toe is ignored. Effective soil pressure at the exterior end of the slab. This is to be noted. 2.8 kg per square foot was an ordinate here at the tip of the toe. Okay, and this will be multiplied by 1.6 in order to determine the ultimate pressure of the soil. The total pressure, as you've seen in the previous slide, was equal to this thing: 0.46 on the heel side and 2.8 on the toe side. And there was a and you know that the size of toe is 3.25 feet. So this pressure, this part of the pressure, you can see the mouse. This pressure is basically acting upward on the toe, and this will cause bending moment in the toe, and the reinforcement will be provided on the bottom of the toe from this bending moment. You know this ordinate is 0.46. This is 0.46, this one. The total, this ordinate is 2.03. This can be calculated from, it's very simple. This ordinate at the interface at the interface of the arm and the heel, this location, arm and the toe, sorry, this location, this location. This can be very easily calculated. This ordinate is 2.03 because this ordinate is 0.46 and this is 2.8. This distance is known to us, so this ordinate can be calculated. 2.03 is this ordinate and 2.8 is this ordinate. So this is a trapezoidal kind of pressure from the soil acting in upward direction. You would have calculated shear force and bending moment diagram for a trapezoidal load. You can do so in this case, or otherwise you divide this into a rectangular pressure and a trapezoidal pressure or rectangular triangular pressure. If you draw a line from this point, then this will give us a triangular and rectangular distribution like this. This is the total 2.03. If we draw a line from this location to this, like this, so this ordinate is 2.03 and the remaining 2.8 minus 2.03 will be 0.77. Okay, this total ordinate, now you look at the figure in the right bottom. This is the toe. This is the junction of toe with the arm. Okay, this ordinate was 2.8. 2.8 multiplied by 2.8 multiplied 1.6. This is 4.48. Now this is 4.48. Total 4.48. This ordinate is 2.03. 2.03 multiplied by 1.6. This is 3.24. So this ordinate is 3.24. Now we will draw a line like this. So one rectangle will be 3.24. 3.24 multiplied by this distance 3.25 will give us the weight acting in upward direction. And then the remaining part, 4.48 minus 3.24 will be this ordinate of the triangle 1.24. 1.24 multiplied by 3.25 divided by 2 will give us another weight. So if you want to calculate shear force and bending moment now from this diagram of the trapezoidal distribution of the soil pressure acting in the upward direction on the toe, we can calculate this easily. Okay, loads on the heel. Loads on the heel are uniformly distributed, acting downward. This is weight of the backfill, weight of the backfill, and weight of the heel itself. Both shall be taken into account in the calculation of bending moments at the edge of the heel, at the junction of the heel with the arm. The self weight of the heel can be calculated from this equation 1.2 into gamma of concrete H times B. B is taken as 1 foot. And B is this 1.5 feet, which is the depth, thickness of the heel. Okay, and factor of earth fill load. H fill, you know, it's 13.5 feet is the backfill on the heel. This is the height of the backfill, and 1 foot is the into the along the length of the retaining wall. This 1 foot is taken, and 1.6 multiplied by 0.12, the density of the soil multiplied by 13.5 into 1 is 2.592 kb per foot on the heel. This is the backfill weight. Factor of surcharge load is also taken into consideration by taking into consideration the effective height of the surcharge. Total factor load comes out to be 3.5 kb per foot, and this is uniformly distributed. And so for this uniformly distributed cantilever kind of beam, you can very easily calculate shear force and bending moment diagram, and for that, this heel will be designed. Now, on the loads on the arm can be calculated very easily. You know that PA is the resultant force. We can write down, if you want to write down PA in terms of H of the, which is the height of the backfill, we can do so very easily in this form. And for every value of H, for any value of H, we can very easily calculate PA. So, and Y can also be written in terms of H. Then the ultimate bending moment can be written in the form of H. And for every value of H, bending moment diagram can be calculated. This can be drawn very easily, like this bending moment diagram. And this is a shear force diagram. Shear force and bending moment diagram can be drawn for distribution very easily. is the shear force bending moment diagram. Okay, for the analysis of toe, as I said earlier, that this is the trapezoidal distribution of the soil pressure in the upward direction. You can determine the load either by trapezoidal area, which is 4.48 plus 3.24 multiplied by 3.25 divided by 2. This will give you 8.3 kip. This will give you not 8.3 kip, less than this, because this will be the pressure at this will be the shear, reaction at the face of the arm, which is the junction of the toe with the arm. However, at a distance of d from this face of the arm, this will be equal to 8.3 kip. This you can do very easily. Similarly, in the case of heel, the shear force at the distance of d can be calculated because the total will be 3.5 into 5.25. The total shear at maximum shear at this location will be 3.5 into 5.25, and at the distance of d can be calculated from the shear force diagram easily. Okay, now let's do the design of arm for flexure. We have seen that for h is equal to 13.5, mu is equal to 45.49 feet from the bending moment diagram. And the minimum reinforcement, according to this equation, is 0.51 inch square per foot. If we given by this minimum reinforcement, we can do so when we calculate small a from this AS and then substitute this small a in this equation. AS minimum is calculated. This will give us a 5 mn equal to 335.2 inch kip per foot. And then we will compare this with the given bending moment. We can see that the 5 mn value, which is in foot kip 27, and the demand is 45.49 at the base of the arm. So demand is more than this nominal capacity. We will have to do some trials in order to calculate AS for corresponding to this bending moment. When we do some trials, you can do this very easily. You assume small a and calculate AS. Finally, you will reach some value of AS, which will not increase with further trials. This value can be selected as AS is equal to 0.846 square inch. And if we try number 8 bar, with number 8 bars, 11.17 inch spacing will be required in order to prevent the failure of the arm or stem against this bending moment. The maximum spacing for main steel reinforcement according to the ACI code is 3 inch or 18 inch. So 11.17 inch is less than this, that is okay. Because the bending moment will change along the height of the retaining wall. For this reason, it is advisable to use different spacing of the vertical reinforcement in order to make the retaining wall economical. In most of the cases, the reinforcement is changed to change from the mid height of the retaining wall, or in some cases it is changed it is changed in three. The reinforcement is provided in 3 different stages. In the first 1/3 part from the bottom of the base, a closer spacing is provided. Then in the middle third of the arm or stem, the reinforcement with the little more spacing is provided. In the top, relatively more spacing will be required. So in this way, we can economize the retaining wall. In this case, however, we have provided only 2 spacings in the arm or stem. And this we have demonstrated in this slide. The depth of the retaining wall from top to bottom are 0, 3, 6, 9, 12, 13.5. The thickness of the retaining wall corresponding to every height. The thickness of the arm corresponding to, that at the top, the thickness is 8 inch at 3 feet. At every depth, this thickness of the arm can be calculated. The moment can be then calculated from the equation because the equation is being written in terms of h. So for any value of h, the bending moment can be calculated. AS minimum can be calculated from the equation. AS minimum values will change because the thickness of the retaining wall changes. along the height of the retaining wall, along the height of the arm. And phi m minimum can also be calculated from this AS minimum, as demonstrated in one of the slides. And then you can see from this yellow that the governing moment will be the nominal, the minimum bending moment, because these are the demand. This table, the column number 3, gives us demand at various heights. So 0 is demand at top, 14.89 at 3 feet, 73.36 at 6 feet, and 196.09 at 9 feet. And the corresponding nominal, the minimum reinforcement flexural capacity is given by this minimum reinforcement. So this is 58.81, which is greater than 0, 98.9 and greater than this, 149 greater, 210. Governing moment means that all these nominal, the minimum capacity in all cases is greater than the demand in every case. So for these, from 0 to 9 feet, minimum reinforcement is enough. Okay, this is what we wanted to clarify in this discussion. And from 9 to 13.5 feet, then the bending moment is more than the minimum, then the demand bending moment is more than the bending moment given by the minimum reinforcement. Okay, for that we will design. And we have already designed this for the bottom 13.5 feet bending moment, which is 545.87 bending moment. For this we have already designed, and we have calculated reinforcement 0.846. The spacing came out to be 11 inch. Maximum spacing is 18 inch according to the ACI code. Now we will keep this spacing uniform from 13.5 to 9 feet from the bottom of the arm up to a depth of almost half of the retaining wall in half of the arm. And in the top portion, we will double the spacing in order to economize the arm or stem. So finally, from a depth of 13.5 to 9 feet, we'll provide number 8 at the rate of 9 center to center, and the remaining top part, we will double the spacing. The horizontal bars on the back side can be calculated from this equation as demonstrated in one of the slides, that it will be equal to 0.0025 BH for deformed bars larger than number 5. So 0.0025 12 into 15, this comes out to be 0.4 square inch per foot. When we try 3 by 4 inch round bar, so 3 by 4 inch, the rate of 11.73 inch center to center will be required. We round this to 3 by 4 at the rate of 9 inch center to center. This is the horizontal reinforcement on the back side of the arm. This is the top, this is the front side of the retaining wall. The reinforcement is 0.0015, 0.27. If we use 3 by 4 inch round bar, the spacing comes out to be 19.5 inch, but this shall be not more than 18 inch, so we will provide this at the rate of 18 inch. Similarly, we can also check the arm for shear. We have seen in the shear force diagram that we use 7.6 kip with 5 EC equal to 15.09 kip. This is greater than 7.6, so there's no problem of shear. The reinforcement in the arm will be provided in this manner. Up to the mid height of the retaining wall, number 8 at the rate of 9 inch, and then the spacing will be doubled with one bar made continuous and the other curtailed at this location. So this will double the spacing in this manner. The horizontal is number 6 at 9 inch. The front side vertical reinforcement is number 6 at 18 inch. Now the design of toe. You know that the design of toe, in the design of toe, the upward pressure of the soil is being taken into account, and MU is being calculated in the analysis part, which is 258 inch kip per foot. AS minimum is calculated from this equation, which comes out to be 0.592. From this, the bending moment given by this minimum reinforcement is calculated, which is 451, and this is greater than MU, so we will use the minimum reinforcement, and minimum reinforcement is 0.592. If you use number 8 bar, the spacing required is 16 inch, which is greater than 18 and all this, so this number 8 at the rate of 16 spacing is enough. For shear, in the shear force diagram, we use equal to 8.3 kip, 5 EC, 17.5, 1 kip. So toe is also safe against shear. Otherwise, you will increase the thickness of the toe. In the heel, the bending moment has been calculated 578.8 inch cape. Base minimum is this. 5 mm from the minimum reinforcement is 451, which is less than this. So we will calculate area of steel. And for this bending moment MU, when we calculate area of steel, it comes out to be 0.75 square inch from height and trials. If you use number 8 part, this will be number 8 at the rate of 12.39 inch. So finally, we will use number 8 at the rate of 12 inch center to center. Supporting bar will be placed number 4 at the rate of 15 inch. Against shear, 14.14 kp is from the shear force diagram, 5 EC, 17.51 kp is more than this. The development length checks are also made at the end. You can see this, that development of the hook must be this. So this is calculated 17.8 inch. This is greater than. We can increase depth of or change the steel grade if we use grade 40 steel. So this will be. So at this, this concludes the design of the retaining wall. You can see different parts of the retaining wall. This is arm and this is heel and toe. In the arm, on the back side, the main reinforcement number 8 at the rate of 9 and number 8 at the rate of 18 provide. Horizontal bars, both in the front and back side, have been provided at the net number 6 at the rate of 9 inch. Okay, and the front side vertical reinforcement number 6 at 18 inch. The top side of the heel, is a reinforcement equal to number 8 at the rate of 12 inch. The bottom side of the toe number 8 at the rate of 16 inch. All other reinforcement is being provided at the rate of number 4 at the rate of 18 inch center to center. This is the end of this presentation. There are few pictures at the end which we can share with you on the actual retaining wall that we have designed and constructed in our projects. This is a typical key provided in one of retaining walls. You can see key in the retaining walls. The retaining wall key, and this is the heel side and this is the toe side. It's very clear. Okay. Next, I will also share with you one of our projects where we have done an assessment of retaining wall in Tantiagal in the Chief Minister House. We then retrofitted this retaining wall, which was basically very weak against sliding, and also this you can see. This is the Chief Minister House in Nathiagali. You can see the sliding of the retaining wall, slight tipping of the retaining wall on this side, which is cracked. The building as well. This separation of the retaining wall, which has caused cracks in the adjacent buildings. So we did the analysis of this retaining wall, and then we suggested retrofitting strategy for this retaining wall. You can see the quality of. You can see this weep hole, which is already choked by vegetation. This needs regular maintenance. So this retaining wall was checked against all possible failure modes, and it was found that the retaining wall was not adequate against sliding, as well as the structural components, especially the arm of the retaining wall, was not adequate against flexure. So we strengthened this proposed retrofitting scheme for CNW department. This was a very good project. So with this, our course in reinforced concrete design ends. If you have any questions, you can ask your questions. Otherwise, the lecture is over. Thank you very much. Any question from anyone, please? Any question?
Sir.
Ji, please. What is your name?